Hello again, AC Science students. This video is for Monday, December 21st. So you're getting this video, of course, because you were not in class. So if you're checking out this Edpuzzle and working through. Main goal today was to turn in the Tectonic Investigation 3. That is due today. If you've not yet turned that in, get that done and turned in. Again, turn it in. Again, in class, we went through and talked about the answers to all that stuff and made sure we had the right understandings in there. Kind of getting ready for our quiz tomorrow for Tectonic Investigations 1 through 3. So that quiz is tomorrow. Please make sure you're in class tomorrow to get the link. I will not be posting it on PowerSchool. You have to be in class to get the link to the quiz and talk to me before we start. So that's where we're headed tomorrow. Of course, Wednesday is our asynchronous day, so that's just a current events article. Find something interesting. There's lots going on, from the conjunction of Jupiter and Saturn to today being the solstice, to there was an eruption of Mauna Kea in Hawaii last night at like 9:30 at night. So lots going on in the news. Find an article that's of interest to you, some that related to what we're studying currently, and fill out the form and turn that in for Wednesday. So today, again, we basically went through and talked about kind of three main sections here. We're talking about thermal energy. How does thermal energy move around the Earth? First section kind of deals with opening it. Second section is the relationship between heat flow and plate boundaries. So as you look at those plate boundaries, what we see is that at divergent boundaries, map legend, again, the redder it is, the hotter it is, the purpler it is, the colder it is. So this is very hot, and this is very cold over here. But that along that green boundary, that divergent boundary where plates are moving apart, is where the highest heat flow is. What's something that interesting that happens in particular over here in the Pacific, off the coast of South America, is that at a convergent boundary, we have this line where all of a sudden it's very, very hot, of course, because this is a divergent boundary, and all of a sudden it switches to crosses this convergent boundary, and all of a sudden it like shuts off. It goes from red to blue here, from very hot to very cold very quickly, and simply by crossing that boundary. So there's an interesting phenomena happening here that's worth exploring. So one of the things we talked about in class today was some resources for you. So this is the textbook. This is chapter 1, section 3 is all about convection in the mantle. So that's the big thing about that heat flow. You have to be able to talk intelligently about convection. Through which heat can transfer radiation, that's like the sun rays on your feet. Conduction, you touch the hot sand, it hurts your feet. Convection is the movement of material, whether that's air or water, or in this case, rock, the actual earth itself. Okay, so convection currents within the mantle. Again, a convection current happens when we've got a heat source on the bottom that expands and rises and moves up to the top. And as it rises, then cools off and eventually sinks back down. And so these convection currents are happening because, of course, the further in you go, the hotter it is on our planet. And so we got some of these nice big convection currents happening between the lithosphere and the stenosphere. Again, three main sections of the Earth. So there's this is still chapter 1. Go back to section 2. Which is all about Earth's interior here. So this is really, we're looking pages like 12, 13, 14, 15 here, about the crust. That's kind of the rocks as we know it, those hard things. And again, this page here, page 14, really goes into detail on the lithosphere and the asthenosphere, which is really what we've been talking about. Lithosphere, again, rocks as we know it. Asthenosphere, those rocks they're still rocks, but they change because of the heat and pressure into, they're almost like, they bend like metal, kind of, or things like silly putty kind of thing. But because of that heat and pressure, they're different, and so they're able to flow more easily. Okay, and so that's where we're looking at this convection currents inside the Earth. Other useful resources, as we talked about, they are the high heat sources tend to be along divergent boundaries, like this one in the mid-Atlantic and this one off in the East Pacific Rise. And so again, what's happening here is that hot molten material is pushing up and spreading out. So it gets hot, it bubbles up. Think of a lava lamp, and cools off as it goes. Okay, so that's happening at those divergent boundaries because it's pushing up and spreading out. And then if we get to convergent boundaries at a deep ocean trench, for example, we get this process of subduction. So this is a convergent boundary. This plate's moving that direction, this plate's moving that direction. Of course, one's kind of slips down. So this one has cooled off enough that it's sinking now back underneath the other plate. Okay, and so you can see again, here's where it bubbles up and pushes out and sinks back down, forming that convection current around. So this is page 84, where they talk about subduction. And that again happens along deep ocean trenches, kind of along convergent boundaries, worth having in there. Page 90 here goes through and kind of talks about some of the basics. Again, nice picture at the bottom here. Again, at the hot spots, it bubbles up and pushes off through. There's actually two convection currents here. Here's one over here, another convection current over here. Think of it like a conveyor belt. Pushes up through, and as it scoots across, it cools off, and eventually it sinks back down to get warmed back up and then come back around. Same thing on the other side. Okay, it warms up, bubbles up through, cools off, sinks back down, and warms back up, comes back up through, and kind of cycles through there. So some good resources in your book here, definitely worth checking out as you go. So in terms of the answers, what's happening at these kinds of boundaries, you have to talk about convection currents here. Okay, why do oceans have high surface heat flows? Talk about that seafloor spreading. Talk about how that asthenosphere is bubbling up and pushing out and spreading out. Deep ocean trenches is where it cools off. That's kind of what we need, which is where they join with the continents. Okay. The next section investigates age of the ocean floor. And what we find is that the ocean floor tends to be the oldest, kind of along the middle. So this is the oldest section, and as we get to the outside toward the continent, this tends to be the oldest. Some relationships that we need in here. If I look at investigation 3, the middle is the youngest, the hottest, and the shallowest. So that's what we see in this thing, is that it is the shallowest, only about 1,000 kilometers deep there. Okay, as it gets older, it gets yellower, out here it's only about 50 million years old, whereas in the middle it's only about 10 million years old. So out here it's 50 million years old. Old, deep, and cold go together. So in terms of relationships that are important that you need to know, old, cold, deep, hot, shallow, young. Those three things go together. So make sure you've got the right three things together. On the quiz tomorrow, I'll be asking you about this relationship. Okay. The last section deals with this idea of hotspot volcanism and volcanoes. And traditionally, typically, when we look at volcanoes, we think about the line of volcanoes. So like up here, here's a line of volcanoes that happens at a convergent boundary. Who's convergent? Okay, or even in like the Pacific Northwest. Oops, right. Here is a line of volcanoes that is a convergent boundary, but that's not always the case. There are also these hotspot volcanoes that more kind of, again, the asthenosphere bubbles up and pushes through. These ones are happening because this plate is sinking underneath the other one, and some of it is light enough that it has to float back up. Whereas these ones, it's actually strong enough to push up through that layer of crust. So there's lots of these around. It's worth finding them. There's a bunch of them in the Pacific plate. There's a bunch also in the African plate. These are the two plates that have the most hot spots in them. You can see, look at all these in the African plate. And to understand what's happening here, we need to think about, my example is always pizza crust, and if I turn these global plate vectors. So what this shows us is that the Pacific plate is moving kind of a northwest direction, and because it's so long, that tells us it's moving very quickly. Whereas if I look at North America, it's kind of moving in the southwest direction, but it's not moving very fast. It's kind of slow by comparison. So at the Pacific plate, it is moving very, very fast, and that leads to a lithosphere thickness, that's what I just turned on, to be very thin. If you look at the legend, the redder it is, the thinner it is, the purpler it is, the thicker it is. So here, I mean, obviously right along here where it's pushing out through, very thin. In the middle here, it's still fairly thin. If we compare that to like South America here, or even parts of North America, is very thick, and not many volcanoes over in this area, of course. Okay. So with the Pacific plate, think of like bread dough. If you push it really fast, it spreads very thin and it's very easy to poke through. If you have a whole wad of bread dough, it's hard to poke through the whole wad, right? But if you spread it real thin, real fast, it's going to stretch and probably break, and that's what's happening here. Whereas if I look at Africa with also lots of hot spots, look at that plate vector. It's teeny tiny, nothing to it. I mean, South America's got bigger plate vectors, but doesn't have nearly as many hot spots. thing with Africa is it's rotating. Look at the as it goes around here. It's kind of twisting. So again, think of your bread dough. If you take it and you kind of push it in two different directions, it's going to twist and turn and tear and make holes, which is sort of what's happening here, and allow that asthenosphere to bubble up through the lithosphere. So this is that's what's happening at these particular locations. Okay. Hopefully you got that all finished, all followed through, answered all the questions. Again, should have gotten the ages on these as well, and talked about that relationship that old, cold, and deep go together, as well as young, hot, and shallow go together, and turn this document in. Again, tomorrow we do have that quiz. Don't forget, if you're on track A, today, Monday, is your weather day. Please make sure you record your weather observations for today. Other interesting things to look for tonight, look for the moon anytime after 1 o'clock this afternoon is when it rose. But also tonight, look for the conjunction of Jupiter and Saturn, kind of just about an hour after sunset. That's going to be your best viewing option. Look kind of to the southwest is where you want to look for that one. Those two planets will be very close together. If you do have binoculars or a telescope or anything that can magnify what you're seeing in the sky, definitely look through that and take a look. It's certainly worth looking at if you have the chance. Otherwise, hopefully you're ready for